All right. Good afternoon. Um, any question before we start? So let me first go over some of the problems that we had on prerequisite exam. Just have a quick review on that, and then we'll start to continue on the lecture, which is about effective math. The first problem that we are going to use its application on vibration. I ask you to find a particular solution for this differential equation. It's a non-homogeneous second order. It's a second order because it has this one, and it's a non-homogeneous because the right side is not equals to 0. When we have non-homogeneous, the total solution is the summation of homogeneous plus particular solution. So our job is finding the homogeneous solution and particular solution and add them up. It's going to be the total solution. So y is going to be a function of time, which is our variable. So it's varying with time. I will start with the homogeneous solution. So I'm looking for solution for this. This equation, we will see this equation maybe in 2 weeks. It's about equation of motion for free vibration of mass spring system. So we assume that the solution, the homogeneous solution, is going to look like e power at, a times t, and we plug in here and set it equals to 0 and solve for a. So if y is e power a times t, first derivative is going to be e power a times t, and second derivative is going to be a squared e power at. So if I plug in here, I will get a squared e power at, 3 times this, plus 2 times this, equals to 0. Good? I just found the second derivative of this first derivative and plugged in the original equation. So since the right side is 0, I can cancel out both sides by e power at. So it's a common term. So I'm going to get a squared plus 3a plus 2 equals to 0. It's a quadratic equation. Solve for that. A would be -1 and -2. So homogeneous solution is going to be C1. C1 is constant. So e power -t plus C2e power -2t. The homogeneous solution is going to be the summation of these two individual roots that we could get from this equation. Good? This is for homogeneous. You have seen this in differential equation course. Any question on this? All right, for particular solution, it depends on the function that we have on the right side. So e power t is a common function that we can have. So we can assume that our particular solution must be a function similar to this function that we have on the right side, except it should have a constant coefficient at the back. By plugging this in the original function, I'm solving for this big A. So if particular solution is A times e power t, then first derivative would be A e power t, and second derivative would be A e power t. So the derivative of this is going to be same, and second derivative is going to be the same. Just plugging the A e power t plus 3 times y prime, so it's going to be 3a e power t plus 2a e power t. This summation should be equal to e power t. So these are the same. So 1, 3, 2, 6, a e power t equals to e power t. So if you cancel out these two, 6a would be 1, a would be 1 over 6. So the particular solution would be 1 over 6 e power t. So this method that I used is not applicable for all functions, but here e power t was some specific function. I could use this method. So if you have other function than e power exponential function, there are some other methods, but it's out of the scope for this one. So that's the total solution is going to be c1 e power negative t plus c2 e power negative 2t plus 1 over 6 e power t. Any question on this? All right. We want you to go over problem 2, which is integration by parts. No? All right. And the inverse of the matrix, almost all of you could answer this question correctly. So I'm not going to go over that. Just let me look at problem number 4. So we are given with two imaginary numbers. So we would like to write this in a format of A or R, whatever. E power I theta. What would be the R? And theta, which is representing this number. So we know that R E I theta it's going to be equals to R cosine of theta plus I sine of theta. So it means this term is going to be equal to this one. So if these two the same, 2 must be equal to the R cosine of theta and sine of theta must be r sine of theta must be equals to 3. So two equations to announce if I square both sides, 2 power 2 plus 3 power 2, I will get r squared cosine squared plus r squared sine squared. I take out r squared from these two terms, I'm going to get cosine squared plus sine squared, I will get r squared. So r would be square root of 4 plus 9 square root of 13. Which is 3.61. And this one, if I divide this by this, I will get r sine of theta divided by r cosine of theta will be 3 over 2. Cancel out r. The tangent of theta would be 1.5. Theta would be the tangent inverse of 1.5, which is 56.3 or 180 plus 56.3. Which angle is the right one? Just one of them is the correct answer. Which one? Why? Because both angle is going to give me the tangent equals to 1.5. But we know that r sine of theta for the angle must be positive. R cosine of theta must be positive. R is a positive number always. So sine and cosine both must be positive. This is the angle which has sine and cosine equals positive. This one, both sine and cosine are negative. When you divide them, you will get the positive 1.5, but this is not the correct angle. So this one is the correct angle. So it's going to be 0.98 radian. So if I want to write this in this format, it's going to be 3.61 e power 0.98 I, or I times 0.98. Good? We are going to use this. And this one, same approach. S square root of -1 square plus -1 square. This is -1, -1. This is going to be a square root of 2, 1.414. And tangent inverse of -1, -1 divided by -1. It's going to be tangent inverse of 1. It's either 45 or 180 plus 45, 225. So since both are negative, the correct answer is 225 or 3.93 radian. So this one is gonna be 1.414 e power I 3.93. Any question on this? So before we start the lecture, just one quick thing. It's a difference between momentum area or momentum or mass momentum inertia. Suppose we have a disk with the radius, it's a disk. With the radius of r, it's rotating about this axis, z-axis. If I ask you what would be the momentum area for this cross section, you look at that and say p pi d power 4 divided by 64. This is a momentum area. It depends only on the geometry of the rigid body. But mass moment of inertia, it depends on the mass as well as the geometry. So for this one, it's going to be half of m mass r squared. So suppose if it's running at the angular speed of omega constant, it's rotating at the angular speed of omega. I ask you find the kinetic energy of this system. You can write half of Im omega squared, and Im is the mass moment of inertia. It's similar to the mass, but for the rotational system, we are using the Im instead of mass. And velocity has been changed to the omega for those rotational systems. So it's going to be half m r squared times omega squared. Or at the second Newton's law, the torque is going to be Im times the alpha. Alpha is the angular acceleration. If it's rotating at the variable speed, then you are going to have the alpha. So how much torque do you need to rotate that? You can find by this equation, but you should use Im. Good? You have seen these terms before. We are just reviewing to make sure that you don't get confused. All right, we talked about effective or equivalent stiffness, and now we are gonna talk about equivalent mass. Let's first look at the definition of effective mass through this example. Then I'm gonna write the definition on the board. We are going to talk about the equivalent mass. So for the stiffness, when I asked you to find the equivalent stiffness, there were three methods that we could use. One, use the parallel springs in parallel. How can we find the equivalent stiffness? Springs in series. How can we find the equivalent stiffness? And using the energy method, which we use the potential energy for original system. We set it equals to the potential energy for equivalent. We solved one example. We use this equation to find the equivalent stiffness. We are gonna on homework 1, you are gonna use this for some of the homework 1 and homework 3. You are gonna use this equation to find the equivalent stiffness for the system. For mass, we are gonna move from potential energy to kinetic energy. And we said the kinetic energy of original system must be equal to kinetic energy of equivalent system. So consider this system. This is a rod. We assume it's a massless. This rod is massless. So we have 3 concentrated mass application A, B, and C. And this rod is rotating at the constant speed of omega. So 3 mass is located at the distance of L1, L2, and L2. So this system has a kinetic energy when it's rotating. The speed of mass 1 is x, if this is x dot 1, x dot 2, and x dot 3. We would like to replace this original system with the equivalent one with a mass, with one mass, located at any desired position. Here we would like to put our mass in point A. Now the question is, how much would be the equivalent mass to represent the same original system? This mass can be at any desired position, but I just put it at position A. So this is what we want to find. So if I want to write the definition for equivalent mass, equivalent mass can be equivalent inertia. If we are talking about wind turbine, which is pure rotation system, the mass is going to change to the inertia. So mass moment of inertia instead of mass should be applied for this system. So in a system connected with a system of connected masses joined by rigid links. So in a system of interconnected masses, these 3 interconnected masses by a rigid link. This rigid link can be shaft, rod, or something like this. Gears. The motion of various mass can be expressed by at some specific point. In this example, the specific point is A. And kinetic energy of the system is given as half of m equivalent x dot square. So when you replace the original system with the equivalent mass, you can represent the kinetic energy of original system by this. So if this is x1, x2 dot, x3 dot, I can replace the original system with this. Is that clear? So now we will see how can we find the value of equivalent mass by using the equation that I explained, setting up the kinetic energy for the original system, set it equals to the kinetic energy for the effective or equivalent system. So kinetic energy for original is half of m1 times the speed or velocity of this mass, which is represented by x dot 1. m1 x dot 1 squared plus half of mass m2 times x dot 2 squared mv squared plus half of m3 x dot 3 squared. So this must be equals to the half of m equivalent x dot squared. In this specific example, x is at the same position of point A, so x dot would be x dot 1 squared. But in general case, point A, this mass can be at any desired or a specific point, and kinetic energy of the system should be written about that point. Any question before we do the class activity? So by working on this equation, I'm going to find equivalent mass. So if this bar or rod is rotating at the speed of omega, velocity of omega, constant velocity, angular velocity, what would be the speed of mass A, B, and C in a term of omega? This rod is rotating at the velocity of omega. Okay? I'm looking for a speed of this point, point A, point E, and point C as a term of omega.
Translational velocity, not rotational.
Rotational is omega for entire of this system. Any point. Yes, because I'm looking for x dot 1. What is the velocity of point A? Translational, not the rotational. Is that clear? Number 4. What do you think? For point A, let's start with point A.
Viscosity will be omega times L1.
Omega x dot, which is representing the velocity of point A, is omega times L1. Different out. Any different idea? The answer is correct. If you have a point which is rotating at the angular velocity of omega, at any time the translational speed is going to be r, which is the radius of rotation, times omega. So what he did, he just multiplied the radius of rotation by omega. So we got x dot of A equals to L1 times omega. Any question on this? Alright, so velocity of point B, same logic. It's going to be L2 times omega, and velocity of point C is going to be L3 times omega. Velocity of point B is x dot of B, or x dot of C for how fast x is changing with time. Good. For this system, and velocity of point A is same things. L1 times omega. So now, back to this. Half of M1, I'm going to replace x dot by omega times L1. half of M2 H dot of V is going to be L2 omega squared plus half of M3 times L3 omega squared equals to half of M equivalent. X1 is L1 omega squared. So this equation is gonna tell us how much would be, what should be the equivalent mass for this entire of the system. So I have half, 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 and half. I can cancel them out. If I square them, I'm gonna have omega squared, omega squared, omega squared, omega squared. I can cancel out all omega squares. So what I'm gonna get, M1, L1 squared plus M2, L2 squared plus M3, L3 squared equals to M equivalent, L1 squared. So I'm looking for M equivalent. So M equivalent would be this divided by L1. So it's going to be L1 squared. M1 plus M2 So if you want to replace the original system with the equivalent mass locating at point A, the magnitude of the mass must be this expression. Question on this before we move on to the next example. All right. So this is the system for rocker arm mechanism for the valve. So this is the valve spring. This rocker arm. Here we have cam and follower, which you can use for timing of this valve. You can shape this cam such that to get the desired timing for this valve, it can be open at a specific time and it can be closed at the desired time. So this is cam, this is follower. We have a push rod here with the given mass. We have one rocker over there, and we have a valve here with the mass of MV. So, and one spring, which is the valve spring. So we would like to model this entire of the system from here as a one equivalent mass and a spring. So the question is, what should be the value for equivalent mass? What should be the value for equivalent spring? I will start with the mass, and then we are gonna do the spring as a homework. So this is the system that we have. We would like to K effective or equivalent. So this original system should be modeled by cam, follower, and spring and mass. So we would like to find the value for K equivalent and mass equivalent. Is that clear? Then when you want to do the vibration analysis of the system, instead of looking at that one, you will look at this simple system. So the terms which they have mass, or at least we consider the mass for them, it's a push rod with the mass of MP. This rocker arm with the mass of R, MR, and also mass moment of inertia of JR or IR. I'm looking at them later. And this valve has the mass of MV. So the equation that we should use is for the mass, kinetic energy. What's the kinetic energy of this system? I defined some coordinates. For the push rod, I defined X, which is representing motion of push rod, and I have XV, which is representing the motion of the valve. And also there is a theta, which is representing the rotation of this rocker arm. So theta R, XP, and XV. These three units. These three variables. XP, XR, and theta R. So XP, the position of, or coordinates of push rod, rotation of rocker arm, and XV, the position of valve. This push rod has a mass of P, so if I ask you to find the kinetic energy of the original system, it's gonna start with the push rod. What is the mass of push rod? It's gonna be P. What is the velocity of push rod? It's gonna be X dot of P squared, mv squared. So whatever is the velocity of this push rod at a specific time, the kinetic energy of that is going to be mp times velocity of push rod, which is x dot p. For the valve, whatever is the mass of the valve, which is mv, times the velocity of valve at that specific time, which is x dot v. So half of mv, x dot v squared. The third term is this rocker arm. This rocker arm is a rigid body with the center of gravity locating at point G. Point G is the center of gravity of rocker arm. The center of gravity, we know that it has a distance of L3 from center of rotation. So this rigid body has two parts of kinetic energy. The center of gravity has the speed. The speed is L3 times omega. Velocity of G, center of gravity. L times omega, same as previous example. So L3 times theta dot R. Theta R is the angle of rotation. Angular velocity is going to be theta dot R. So 1 part of kinetic energy is going to be half of m of rocker times velocity of center of gravity, which is a square. L3 theta dot R square. At the same time, it's rotating. So at the angular velocity of theta dot R, so another part is half of I with respect to center of gravity times omega squared. We are gonna use this in some other problems and examples. So make sure that you know what I'm talking about. So the rigid body has, it's not a point, it's just a rigid body. So for the kinetic energy, you should look at the center of gravity. Center of gravity has a speed, translational speed, as well as rotational. So we should consider both. The center of gravity is moving, so it has a speed. Also, the system is rotating, so it has. We should consider the rotational, the kinetic energy corresponding to the rotational, which is I times omega squared. Question about this? I mean, this is not tricky, but the point of this example. For the rigid body, you should consider both. Any question? Before I move on, before I continue this example, another way that you can look at this part is finding calculating the mass moment of inertia about center of rotation rather than center of gravity. So if you remember, there is a theorem, parallel axis theorem. I with respect to center of rotation, which is O, is I with respect to center of gravity plus mass of the rigid body, which is the rocker R, times the distance d squared. D is the distance between center of gravity and center of rotation, which is L3. So in this case, it's going to be mr L3 squared. You either use the center of gravity to write the kinetic energy, or assume that we only have pure rotational, so we write everything with respect to center of rotation. So forget about this part. We say that this entire of this is going to be half of I, not center of gravity, center of rotation, omega squared. These two are the same. If you plug in here, we will find that these terms is going to be equal to this plus this. Here we wrote kinetic energy with respect to center of gravity. This one, we assume that we have pure rotation, but we need to know what would be the mass moment of inertia with respect to center of rotation, and we use the parallel axis theorem to find that. You remember the theorem? We use it in KND. You might have seen it dynamic also. See here, I center of gravity plus, let me just calculate this part. Half of IO times omega squared. IO would be ICG plus MR L3 squared times omega squared. So if I multiply this, I'm gonna get half of ICG omega squared, which is this guy, plus half of MR L3 squared theta dot squared, which is this L3 times theta dot R squared times MR, and this is the half. Good? I'm gonna use this in many examples. All right. So, do you see any other terms for kinetic energy? Any mass which is moving and we didn't consider on this equation? I consider this push rod, and the kinetic energy of that is mass times the velocity square of this one, which is x dot p. I looked at the valve, I consider entire of the valve as the mv, the speed of that is x dot v squared. And this rocker arm, either you use a mass moment of inertia with respect to center of rotation, or look at the kinetic energy for the center of gravity. Either way, you will get this one. So now, this must be equals to the kinetic energy of equivalent or effective system. For that, it's going to be half of M effective or equivalent times what would be the velocity of M effective? What should I write here? V squared. For this one. Any idea? In this example, I'm finding the equivalent stiffness at point A. It means I would like to move or have the system as a mass spring which is locating at point A. So if I'm talking about the point A, then this is going to be x dot p squared. True? I could ask you write everything with respect to any other point, this point P. Then you have to write the speed for that point. Make sense? So when we are talking about equivalent mass, we should specify which coordinates we are talking. This equivalent mass is about this point P. So which makes sense because we moved everything to the push rod position. This location. So now set this equals to this one. Half of M equivalent or x dot p squared. So here I have question on this. Here I have x dot p. Here I have x dot v. I have theta dot omega square is theta dot r, and back there I have x dot p. So how can I get rid of them? Because I should get rid of these terms to find equivalent mass as a term of other constants, which are mp, mv, mr, and I center of gravity. How can I get rid of them? In previous example, it was simple, we wrote, you remember what we did. Velocity of this point was L1 times omega, M2 times omega, M3 times omega. We had omega on both sides. We could cancel them out. Now I should write everything as a one common term, then I can cancel out from both sides. So now look at xb, theta r, and xb. All three variables that I have are dependent to each other. So there you cannot fix this and move point A or point B or vice versa. You cannot fix point B and rotate the arm. So it means these three are dependent. How they are dependent? X dot of P is L1 times theta dot of R. L omega is the velocity of point P. X dot of V is L2 times theta dot. L2 times theta dot of R. And what else? That's all. I mean, now I replace x dot by this, L theta dot. I replace x dot v by this, L2 times theta dot. This is going to be theta dot. I'm going to keep this. This is going to be theta dot. X dot of p should be replaced by L theta dot. Then each term is going to have theta dot. I'll show you we can cancel them out and find equivalent mass. Good? So the rest is just placing this. Half of MP L square theta R dot square plus half of MV this is L1 L2 theta dot square plus half of MR L3 square theta R dot square plus half of I central of gravity theta dot R square equals to half of M equivalent x dot of P is L1 so first I cancel out half from both sides. Theta dot square, it's going to be the same theta dot square, theta dot square, theta dot, and theta dot. Cancel them out. Now I have MP L1 square plus MV L2 square plus MR L3 square plus I with respect to center of gravity equals to M equivalent. So if you have the mass of the pushrod and L1, if you have the mass of the valve and L2, and mass of the rocker R and 3, you can have this mass moment of inertia of the rocker R with respect to center of gravity. You can do the mass and find the equivalent or effective mass for the for this system.
Is there an L1 over there?
Which this
Yeah,
one?
that L1.
Which term?
That L1, the one.
This one?
Yeah.
Thank you. You divide everything by L1 square. I forgot this square. Because It's the x dot p, which is L1 squared. Divide both sides by L1 squared. This one, L1 by L1 is going to be 1. It's going to be L2 divided by L1 squared. L3 divided by L1 squared. And this is divided by L1 squared. Thanks for catching. Any question on this? All right. One of the last problem of homework 1 is about the wind turbine that we are going to go over this semester. So we looked at the drivetrain on very first class. So this is the hub where you can connect the blades at these 3 positions. And this is the main shaft which connects the hub to the gearbox. So inside the gearbox we have 3 stages. One stage for planetary gear, which increasing the speed by this ratio 4.7. The first stage is connected by the shaft to second set, these 2, this small one, gear and pinion. So with the gear ratio of 3.56, and the last stage is going to be this gear and this pinion with the speed of gear ratio of 4. So if you multiply these 3, you will increase the input shaft speed by that ratio, and you will get the highest speed after the gearbox, and it's connected to the generator to generate the electricity. If we model the drivetrain like this, we have a blade which has a huge moment of inertia because 3 blades has been connected to this part. It's a huge inertia. Then we have a low speed shaft which is connected to the planetary gear. Planetary gear have a fixed ring plus this planetary. We have 3 of them. It has been connected to the sun, and the output is the shaft which is connected to the second parts of the gear. It's a gear and the pinion, they have been connected. And then the shaft which connects this one to the 3rd stage, and then we go to the highest speed shaft at the end. We would like the mass moment of inertia for each part has been given. For the blade, for planetary parts, for the sun, for the first set of gear, pinion, and the 3rd stage, gear and pinion. Gear is the greater one, pinion is the smaller one. Also for the generator, the mass moment of inertia are given. The gear ratio also are given here, same as the slides that we have. Now, since each mass moment of inertia is rotating at different speed, we are interested to find the equivalent mass moment of inertia for each component at the blade speed. So, for example, this is the blade, is suppose it's running at 20 RPM, for example. Whatever is the speed of the blade, this gear is rotating at the same speed because it's directly connected to this. So if I'm looking for the mass moment of inertia of these parts at this speed, I shouldn't touch this part. So the mass moment of inertia for planetary, it's gonna be this one, 1116.72. I'm not gonna touch that. Same thing for the blade. But for the sun, this is rotating at a different speed because of the gear ratio. What would be the equivalent IS at this speed? So you should look at that, find the value, and then what would be the equivalent mass moment of inertia for G1? Because these two are rotating at the same speed. What would be the equivalent mass moment of inertia for pinion 1, gear 2, and pinion 2, and also generator? So this is what I'm asking you guys think about that and calculate the value at the blade side. We are going to use this data for future analysis. On homework 3, I'm asking you to look at this shaft and find the stiffness first, the torsional stiffness. And then, since they are rotating at different speed, find the equivalent stiffness at the blade side. Then we are ready to do the analysis, which is going to be homework 5 or 6, I guess, to model this drivetrain by a simple mass and spring. But for now, we are looking for equivalent mass and equivalent stiffness. For this homework, I'm looking for equivalent mass only. Any question about this problem? So the first problem of this homework, for the cam follower example that we did in class, find the equivalent stiffness of the valve spring if it should be located at point A. So I could find the equivalent mass. Now in the homework problem, I'm asking you find the equivalent spring of the system, and I assume that the shaft or the rocker arm doesn't have any stiffness. The only component which has the stiffness is the valve spring. So if it has KV, for example, KV what would be K equivalent of the system or effective of the system as a term of KV if I want to move this to this position? The other problem should be straightforward, but if you have any question, you can ask. All right. Any question on this? All right. I'll stop at this slide and we continue on next week. I already posted the homework. It's gonna do next week.